Now we'll talk about image formation in a plane mirror. And by plane mirror, that's Plane, we mean a flat geometrical plane. So this is just a flat mirror. So let's imagine looking at a mirror, and this is the mirror seen from the edge. So this is the floor down here, and let's suppose that an object is standing on the floor right here. And then we're going to be up here, so this is our eye seen from the side. So that's the pupil there and some eyelashes. That's supposed to be an eye. So like if you're having trouble with that, you imagine the nose and the mouth and the chin there. So that's a face. You're looking this way. So that's an eye as seen from the side. Now, whenever you look at anything, you're looking in a certain direction. And when you look at an image in a mirror, you are looking in a certain direction. And light rays are coming from that direction into your eye. And the image appears to be in the direction in which the rays are coming from when they enter your eye. So what we see down here, I'm going to draw the light rays reflecting off the top corner and the bottom corner of this object. So this is a solid object down here, and light is coming in and striking it, and light is scattering off from that object in all directions. Some of those light rays come and strike the mirror and enter your eye. Let me try that one more time. Okay, and some light rays from the bottom corner down here also come and strike the mirror and enter your eye. So the point I'm making here is that when you look at the image in the mirror, if you look this way, you can see the image in the mirror, but your line of sight goes in this direction, follows the light rays coming into your eye. So if we take these two lines and extend them this way, we end up with a point down here and a point here. The object appears to be over here. It appears to be behind the mirror. And you should be familiar with that. When you get up in the morning and you look at yourself in the mirror, you don't see the image of yourself on the front of the mirror like a painting. It's not like it's right there on the mirror. If you're 2 feet in front of the mirror, then the image of yourself is 2 feet behind the mirror. In other words, the light here, look at this top corner. The light has traveled a certain distance and entered your eye. And you can perceive that. So you see in this direction, that far away would be this point in space right here behind the mirror, such that this total distance is equal to the total distance the light traveled before it came to your eye. And the same thing with the bottom corner. Light coming off the bottom corner goes a certain distance and enters your eye, and in that direction, for that total distance, you see the bottom corner of the box. So the image appears back here behind the mirror. Now, what's actually behind the mirror, who knows? This could be a wall, this could be another room, this could be outside of the house. The point to understand here is that there aren't actually light rays here converging to form an image. This is what we call a virtual image. No image really exists over here. Could be anything imaginable over there, but it appears as if the image is there. That's a virtual image. That's different from what we call a real image. A real image forms where light rays actually converge to make an image. And a good example of that would be a movie screen. If you have a movie screen here and there's a projector over here projecting a movie onto the movie screen, then light rays are actually shining on the screen. And there's lenses and a light bulb producing light and lenses focusing the light on the screen, so you actually get an image in here on the screen. Maybe it's some mountains and some sky or something, but you actually get light rays landing on the screen producing an image on the screen. That's a real image, and it actually exists right there on the screen. That's why we call it real. A virtual image is an image that only seems to exist at that particular location.
Good afternoon, ladies and gentlemen. Today we are going to go over geometric optics. But before we actually start optics, we have to talk a little bit about reflection itself. So, if you look in your packet at the first picture, you'll notice in the top right corner a question about law of reflection. And hopefully you guys remember with law of reflection that the angle of incidence is equal to the angle of reflection, and that all angles are going to be measured from the normal line, which is that imaginary line perpendicular to the surface. So theta 1 is measured from the normal line, as is theta 2. And depending on however the surface looks, remember the normal line is always going to be perpendicular, and the reflection angle will always be the same as the incident angle. Now, this brings us to talking about reflection itself. Now, when we talk about regular reflection versus diffuse reflection, now this is an example of regular reflection, which simply means that all of the lines that are incoming, they strike a perfectly smooth surface. They reflect parallel to each other. So each one of these has a little normal line that's reflecting off of, and it reflects at the exact same angle, and they reflect to a specific location. So only the person who's looking inside this mirror would be able to see the image of whatever is incoming itself. A person standing somewhere else would not see the exact same image. They would not see anything at all, possibly. This is different than diffuse reflection. When we talk about diffuse reflection, the surface is bumpy, and because it's bumpy, the normal line is different at each location. It might look like this over here, and it's going to be completely different depending on what the surface is. But because of the rough surface, the light is going to reflect in all different directions. And because it reflects in different directions, that means that a person at one location is able to see it, and someone at a different location is able to see it as well. And this covers most objects in the real world. The fact that we're able to see each other or able to see anything inside a room means that these surfaces all are rough and that the light is reflecting off the surface into our eyes. So as an example, if you take a look at the right side, you have the pencil. With the pencil, light strikes the pencil. And when light strikes the pencil, it automatically reflects in every direction. And if some of it will just happen to go into your eye over here, meaning that you are able to see the pencil as well. But what does this have to do with optics and mirrors? Well, if you turn to the next page in your packet, you'll see a diagram of a woman who is looking at herself in the mirror. And the question is, why is the woman able to see herself in the mirror? Well, if you look at her shoe, where some light is going to come in and strike. When the light strikes the shoe, due to diffuse reflection, it actually reflects in every direction afterwards. But some of it happens to go out and strike the mirror at such an angle that's actually going to reflect into the person's eye. But the brain is not able to comprehend that light can change direction. So rather, the brain is going to assume that the light had traveled in a straight line. So even though the light goes into the eye, it actually believes that it traveled a straight line the entire time from behind the mirror, which is why we see our shoe inside the mirror. Now, this is not a real image. That's not really there. It's an imaginary line that our brain made up, which is why it's a virtual image. And any part of the woman is able to be reflected by the mirror into the person's eye. So even if it's the briefcase is going to reflect into the mirror and then reflect into the woman's eye. But again, the brain can't comprehend the fact that light changed direction, so it believes it traveled in a straight line and sees the briefcase behind the mirror. This, of course, holds true really for any object that you see, whether we're talking about looking at a bottle inside a mirror or again, looking at ourselves in a mirror also. But an interesting question is, how much of a full-length mirror do you actually need to see yourself? Because when we look at a full-length mirror, normally we see our entire body, and you might automatically assume that we need the entire mirror to see our body. But if you look at the way the reflected lines are drawn, starting from the person's shoe in A, well, when you see your shoe, of course, it had reflected into the eye. And the thing is, if you assume that the mirror is perfectly vertical, then really you only need down to the middle point in order for you to see your foot. All the space underneath isn't used. We see the shoe behind the mirror, but in reality, we're not actually seeing anything being reflected from the bottom half of the mirror. It's just that we see the image inside the mirror. So if the person's at the top of his head, if that goes in and reflects, then that's going to reflect back into his eye as well. So in the end, we ultimately only use the top half of the mirror. With any sort of plane mirror, you have to remember a few important rules. So if we take a quick look at this animation over here, we have a candle in front of a mirror. Okay, and we can see the reflected lines drawn by the mirror inside this diagram. But there's a few important things to note here, okay? Right now, we're going to be looking at the tip of the candle, which is giving off light in all directions. Now, some of the light is going to go down, strike the mirror, and reflect back. But ultimately, when we trace it back, it still matches up to the top of the candle, as well as this line over here is also going to match with the top of the candle, meaning that you have a virtual image that is formed on the other side. And we're going to talk more about drawing lines when we get to curved mirrors. But for now, just understand that the candle, okay, will always have its lines match up on the equal distance on the other side. So the height of the object is going to equal the height of the image, and also understand that the distance of the object from the mirror is going to equal the distance of the image from the mirror as well. So if I were to ask you a question, let's say we have a person standing in front of the mirror, and there's also a chair in front of the mirror. The person is standing behind the chair. The chair is 2 meters away from the mirror, and the person is 3 meters from the chair. So the question is, how far is the image of the chair from the person? We know that there's going to be a chair formed equally distant on the other side. And understanding that the distance of the object from the mirror is always going to be the same as the distance of the image from the mirror. If this is 2, then this has to be 2 meters as well, meaning that the total distance of the person from the image of the chair would be 7 meters. And that's why when you actually look at the reflection of something in the mirror, it might seem smaller. It's not that the size of the image is actually smaller than the size of the object itself. It's just that it's literally further away. So the object over here is only 3 meters away from the person, while the image is 7 meters away, so it's going to look much smaller because it's more than twice as far away.